So we've talked about the glutenin network. Now let's talk about eggs. So for this, let's just consider a single egg. You know when you bake, you put some number of eggs in. And so the question I want to ask is, how many molecules of egg protein are you putting in to the batter when you put in one egg? And I'm going to focus on, just for simplicity, one egg molecule. I'm going to talk about ovalbumin, which is the major protein component of egg whites. You'll remember from earlier in the course when Dave Arnold talked about cooking eggs, that there are a huge number of different proteins that are involved in gelation networks inside of eggs, and they're all playing some sort of a role in baking. And I'm just going to focus on the major one in order to basically inform our thinking about this discussion, and in particular to think about whether or not the egg network can contribute as much to the elasticity as the gluten network. I mean, is this even possible given the numbers of molecules? So okay, so let's think about a single egg. So I'm going to take an egg which has a volume of about 34 milliliters. That's a volume that an egg can have, and that actually corresponds to a weight which is 34 grams, because of course the major component of egg is water, which has a density of 1 gram per cubic centimeter. So an egg white is about 2/3 of an egg, and it turns out that about 60% of the protein in egg white is ovalbumin. So and about 10% of the weight of egg white is protein. So what we have to do is take the mass of the egg white, we have to divide by 10, that gives us the mass of protein that's in the egg white, and then we have to multiply that by 60%, and that basically gives us the mass of albumin. So if I sort of work that out, 34 grams times 2/3, which is the egg white, times 0.6 times 0.1, I find that there are about 1.4 grams of ovalbumin in an egg. Okay, so now ovalbumin has a molecular weight which it turns out is about 45,000. And so to convert that to the number of moles, the number of molecules, what I do is take 1.36 grams, I divide by 45,000 grams per mole, I multiply by Avogadro's number, 6.022 times 10 to the 23, and that gives me, let's see, let me just do this, that gives me 1.8 times 10 to the 19 molecules. 1.8 times 10 to the 19 molecules. That's a lot of molecules in a single egg. Now, we need to compare this number with the similar numbers that we had for gluten. And remember, the way that we did it for gluten is we considered a liter of batter. And so the question that you have to think about is, well, how many eggs would you put into a liter of batter? Now, if you're making bread, you'd put no eggs in. There tend not to be eggs in bread. So in eggs, the answer is 0. So if you're making pancakes or cake, I don't know, I mean, it sort of depends on the recipe, but I would say that in a liter of batter, you would use somewhere between 2 and 4 eggs, probably on the higher side, because a liter is actually quite a bit of batter. So what we have to do is multiply our number, 1.8 times 10 to the 19, by 4 to 8. And that means that in pancakes, by 4, because there are 4 eggs. So so that means that 1.8 times 10 to the 19, that corresponds to about 8 times 10 to the 19 molecules of ovalbumin in pancakes, and about the same number, about 8 times 10 to the 19 in cakes. And if we then convert that to cross-link distances using the sort of arithmetic that we did before, that corresponds to a cross-link distance of about 20 nanometers or so, a little less than 20 nanometers. The number is very much in the same ballpark as the distance that we found before between gluten molecules. Now, there's one more thing that we have to think about to sort of see how this thing is going to form a network, which is we have to figure out how big these ovalbumin molecules are. Now, if you go and look at a crystal structure of ovalbumin, which is in its folded state, it turns out the dimensions of the molecule are about 7 nanometers by 5 by 5. So it's actually pretty small. So if you see the ovalbumin molecules were folded in the batter, if you have something which is about 7 nanometers across and the different things are 20 nanometers apart, they can't stick to each other, right? It simply won't work. I mean, you know, if I'm here and you're on the other side of the room and we try to hold hands, we simply can't do it because our arms aren't long enough to make the different molecules stick to each other. However, you will remember from our discussion of eggs before that the whole point of actually forming a gelation network in an egg is that the protein first unfolds. And when it unfolds, it will stretch all the way out. If you were going to estimate how much this 7 by 5 by 5 molecule is going to stretch out when it unfolds. I mean, one way to think about it is just to imagine that you stretched it way out, and maybe the radius of it when it was unfolded was something like a nanometer or so. And if you ask how long is something which has a cross section of about 1 square nanometer, how long is it going to be? It's going to be something in the range of about 50 nanometers. So these ovalbumin molecules, when they unfold, are about 50 nanometers, which is the same basic length scale that we had for the glutenins, and they will then be able to stick to each other because they're only less than 20 nanometers apart. So the conclusion of this is that at least from the numbers alone, the egg network actually seems quite similar to the glutenin network. I mean, if we think about E is equal to U over L cubed, I mean, the cross-link distance could change a bit, right? They're not going to be exactly the same in the two networks, but they're basically the same order of magnitude. The bond energies are also the same order of magnitude because they're all interactions, hydrophobic interactions between proteins, right? Modulated by electric charge. And so one would think that they have roughly the same consistency at first blush. Now, of course, just to emphasize again, the structure of baked goods is complicated. There's interplay between the glutenin networks, the eggs, and also the starch granules, which we now have to turn. And the way that the elastic modulus is actually determined is by some complex interplay of the three, which we can only imagine. So finally, let's consider the starch granules. So this part is actually much easier. So you'll recall actually, from our earlier numbers with the structure of flour, that we said that 76% of the weight of all-purpose flour is carbohydrates. That's a rough number. Pancakes are about 40% flour, bread is about 60% flour, and cakes are about 30% flour. So that means that the starch percentage of pancakes is 40%, 0.4 times 0.76, that's about 30%. So pancakes are about 30% starch, bread is about 45% starch, and cake is about 22% starch. So those are the percentages by volume that there are of the starch granules. Now, if you remember our discussion of emulsions from last week, these percentages are all below the critical percentage that you need for the granules to actually jam into each other and form an elastic network. So at first blush, it doesn't look like the starch network is going to contribute to elasticity. However, when you heat starch granules in a background of water, they will tend to swell up. You'll remember Dave talked about this, and also Nathan Myhrvold, in the context of reductions of sauces. The starch granules swell up. The liquid then becomes more viscous because the starch granules can now bump into each other. Well, if they continue to swell up, and if the volume fraction of starch granules were big enough, they will actually form an elastic solid. You will actually have this network of grains which are actually jamming into each other, and that network of grains will contribute to the elastic modulus. And indeed, this is totally within the ballpark of something that can happen in all three of these recipes. That is, in pancakes and bread and in cakes, the fraction of starch is within a factor of a couple, of 2 to 3 of the number of the volume that it has to be for it to be able to form an elastic network. And swelling by a factor of 2 or 3 is really not out of the question. So in summary, what we've just done is argued that that the three main ingredients of cake, bread, pancake recipes, namely glutenin, egg proteins, and starch, can actually contribute to the elasticity. We expect from these numbers for them all to contribute to the elasticity in some way, and the precise elastic modulus presumably depends on the way that you mix them, and also the other ingredients that are in the batter, acidic or salts or things like this, which actually can modulate the interactions between them. I think that the fact that all three of these turned out to be important really goes some way, at least, of explaining why the phase diagrams, the bakery phase diagrams that I showed you before, are so robust. The fact is that if you change the amount of flour in a recipe by, I don't know, 10% or so, you're really not changing the distance between the gluten and bonds by very much. You're not changing L, the cross-link distance, by very much. And although the 10% change could affect the recipe, there are lots of things going on after all, it's not obviously going to make a huge effect on the elastic networks that are occurring.